Okay, it's a great pleasure to introduce Roberto Miatello from Universidad Nacional de Córdoba. He will talk about spectra and representation equivalence for space forms of compact symmetric spaces of rank 1. Go on.
Okay, it's a pleasure to be here, and it would be more pleasant even to meet everyone in person. So I will talk today about the work we've done with Emilio Lauret, where we compare two concepts relative to the relative connecting spectrum and representation theory. So part of this can be done in general, but we will restrict ourselves to symmetric spaces of rank 1, and it will be clear why we do that. We'll work only in the compact case. Okay, so give some introduction. We start with the G as a semi-simply group, K a compact subgroup, Lie algebras G and K. We decompose G since by the symmetry condition as K plus P with Kp included in P. So the tangent space of X at Ek is identified with P. So the G invariant metrics on X are in a bijection with at K invariant inner products on P. And we consider the homogeneous metric on X induced by a fixed 8G invariant inner product on G, so that will work with X, a normal Riemannian homogeneous space or symmetric space. Now we fix tau, W tau, a finite dimensionally unitary representation of K. Form the homogeneous vector bundle, we call it E tau, that is G cross tau, W tau, and well, that means that we identify pairs GKW with G tau KW for all G in G, W in W tau, and K in K. So we denote by brackets the class of XW in G in E tau. Now we look at the space of smooth sections, E tau. It is isomorphic as the G module to infinitive G tau, that is functions from G to the finite dimensional vector space W tau that are smooth and that transform according to tau on the right. Then Gx on the left. So the identification, there is a natural identification. Now we look at the universal enveloping algebra U of GC of the complexified Lie algebra GC of G, and the Casimir element has a standard formula involving, so C is the sum of xi square, where the xi is an orthonormal basis of G respect to the given inner product. Now we take gamma, a finite subgroup of G. G is compact, so gamma will be finite. So the space X mod gamma is a compact good orbifold. If gamma acts freely on X, then there will not be singular points. We look at the bundle E tau gamma over X mod gamma defined by the relation, the standard relation for all gamma in gamma and pairs in E tau. So the smooth section of E tau gamma will be identified with gamma invariant smooth sections of E tau. So the Casimir element induces a self-adjoint second order elliptic differential operators acting on smooth sections of both vector bundles, E tau and E tau gamma. And then, well, that, as I said already, delta tau gamma is defined as delta tau restricted to gamma invariant smooth sections of E tau. So the spectrum of delta tau gamma is called the tau spectrum of X mod gamma. And it can be expressed in Lie theoretical terms. So how we do this? We decompose L2 G mod gamma, so we forget about K for a moment, as a sum of irreducible subrepresentations. Each representation will have finite multiplicity as G modules, Gx on the right here. So n gamma pi will be the multiplicity. And this is the right regular representation of G. G hat is the unitary dual. Okay. So now we have an expression for the multiplicity of, we call it mult delta tau gamma of lambda, of a non-negative real number lambda in the spectrum. And it is given as a sum of n gamma pi of the dimension of W tau in V pi. Pi is a representation of G and tau is a representation of K. And we sum over the representations pi such that the Casimir eigenvalue is lambda. So we denote by G hat tau the subset of tau spherical representations of G, that is the pi V pi such that they contain hom K W tau V pi is non-zero. So now we say that two spaces, now we take gamma, gamma prime, and we say they are tau isospectral if the operators corresponding delta tau gamma and delta tau gamma prime have the same spectrum. And gamma prime is said to be tau representation equivalent if now the multiplicities n gamma pi and gamma prime prime coincide for all pi in G hat tau. So from the formula, we see that if the multiplicities coincide, then the manifolds will be tau isospectral. So the converse question is the topic of this talk. So thus, in which cases tau isospectrality implies that gamma and gamma prime are tau representation equivalent, so that when the spectrum are the same, the multiplicities are the same. So more generally, if we have just one group gamma, so does the tau spectrum determine the representation of G on L2 G mod gamma tau? So we will say that in this case, if this holds, we say that the representation spectral converse is valid for G, K, tau with a given inner product. So that will mean that for every gamma, gamma prime discrete co-compact subgroups of G, such that the quotients are tau isospectral, then the groups gamma, gamma prime are tau representation equivalent in G. So we will assume that G is semi-simple and, of course, compact. So we will prove the following result on the strong representation converse. I will sketch. Let G mod K be a compact, irreducible, simply connected, symmetric space of real rank 1. Then there exist infinitely many tau in K hat, such that for gamma prime, arbitrary discrete subgroups of G, if the multiplicities of lambda in the spectra for both groups coincide for all but finitely many lambda, then gamma and gamma prime are tau representation equivalent in G. And consequently, the manifolds are tau isospectral. Hence, the strong representation spectral converse holds for GK tau. So we call this strong representation spectral converse in the sense that we don't need all coincidences, but just all but finitely many coincidences. That's the meaning of strong. So we will describe the strategy of the proof. So we take a maximal torus T of G, the algebra T, and we take the roots, set of roots with respect to a Kaplan subalgebra TC of GC. We take phi plus the subset of positive roots relative to an order on KC. And then the highest weight theorem allows to parameterize G hat by sets by P plus of G's, G integral dominant weights with respect to phi plus. And now we introduce an ordered set S omega lambda naught. All the sets of pi lambda naught plus k omega with k a non-negative integer. And we call this the string of representations with base lambda naught and direction omega. So this will be a main tool in our method. So the idea is that G hat tau, that is the set of irreducible unitary representations of G that involve tau, that contain tau, is a complicated set in general, but it can be decomposed as a union of this type of sets that we called S, the strings. So this is like we are decomposing the tau, the unitary dual involving tau, as a union of like one-dimensional things, the strings. And also we can make the union disjoint. Well, the proof is, so there is an argument that involves the Borel-Weil theorem. So it's not too hard. And then if we assume two strings intersect, then we have lambda naught plus k dab omega equal lambda naught prime plus h omega. Then we can write either lambda naught or lambda prime naught in terms of the other. So one of the strings is containing the other, and we can get rid of one of them. So we can make this to be disjoint. So now we have to connect the strings with the lambdas, with the eigenvalues. So there is a formula for the eigenvalue of the Casimir for representation pi. That's formula 7. It's on the board for each pi given. And then every eigenvalue of that we are involved with of delta tau gamma lies in a countable set, in the countable set of these eigenvalues of the Casimir. Now, another main concept is the concept of tame eigenvalues. So the tame eigenvalues are those eigenvalues that are involved with just one irreducible representation. So the main problem here is that there are eigenvalues lambda that are eigenvalues for very different pi's. And in that case, it seems hard to separate the pi's. So, but tame eigenvalues are nice in the sense that they correspond essentially to just one representation, or eventually to a pair pi star of the pi and the dual of pi. So when the multiplicity of the eigenvalue in that case is it can be expressed easily. And then we want to give conditions on G, K, and tau to guarantee that all but finitely many eigenvalues are tame. So we calculate for pi in a given string. So the highest weight is K omega plus lambda naught in terms of K and omega and lambda naught. So when two representations are in the same string, then there will no coincidence of the eigenvalues. So this is easy to see. So now we have so we denote E omega lambda naught, the eigenvalues of the Casimir in that string. And then we have that E tau, the eigenvalues for tau, is a union of eigenvalues of the set of strings. For now, E tau is infinite. But we need to investigate the coincidence of Casimir eigenvalues for two different strings. So this is our main tool, which is a result that discusses or describes given two different strings, how you see the direction is always the same, but the base is different. And then we want to know when these sets of eigenvalues can have coincidences. Then the condition to have an infinite set is that one of the following conditions hold. So in one case, omega, which is a direction, omega lambda naught equals omega lambda prime naught, and the eigenvalues of corresponding to pi lambda naught and pi lambda prime naught are the same. And the second condition is more complicated. So in case W lambda naught is not equal to W lambda prime naught, then we must have this equality, the equality that's described in 12. Well, to prove this theorem, we need a lemma that involves, you see, we have a geometric condition that involves the projection of lambda naught minus lambda prime naught onto the direction. In the case of the sphere is Sn, so that means the the case of G equal SO2N, then the condition I is the one to look at. Condition 2I it cannot hold. On the other hand, for the other symmetric spaces, we need to look at the second condition as well, at both conditions. Well, I think this theorem we'll mention later. And now, if we assume that G hat tau can be expressed as a finite union of strings, disjoint, and moreover, for any pair lambda prime naught in P tau, which is the set of weights in this where the bases lie, so that for lambda naught and lambda prime naught, conditions I and 2I do not hold unless there is this condition 14 that is rare and complicated. Then all but finitely many eigenvalues in E tau are tame. And then the strong representation spectral converse is valid for G K tau. So this is proved. Once we have that all but finitely many eigenvalues are tame, then we can use a previous result of us on strong multiplicity 1. It is essential that P tau is finite, because in general, the decomposition as a union of strings is an infinite union. But for compact symmetric spaces of rank 1, the union is finite. And then if we don't have those coincidences, then we are in the condition that the I and 2I are not satisfied. And then all but finitely many eigenvalues are tame. And then we are in good shape and we can conclude the result using the strong representation spectral. So then we get the strong representation spectral converse. Actually, one can prove a stronger version, which involves only one gamma. So that the spectrum of the Casimir operator, the tau spectrum, determines the whole spectrum. Okay, well, I would say a few words about odd-dimensional spheres to illustrate. So G is SO2N, and then we take a certain inner product given by involving the killing form. Then we have the roots, the weights. We take the lexicographic order on H star respect to basis, and then we have a system of simple roots that is number 15. Then we have positive roots and the positive weights. We have a max. In K, we take the maximal torus T intersection K, and then we have a basis for KC intersection GC, and So we have weights for K now, and then we have a branching law, and then if we have a weight mu for K written in terms of epsilon j's and a weight lambda written also for epsilon j, but from 1 to n, then tau mu occurs in pi lambda restricted to K if and only if there is that those conditions. The A's and the B's satisfy such condition number 16. Now, in all cases, dimension is 1. Tau mu appears in pi lambda restricted to K once or 0. So then we have a lemma, and then so this is a lemma that is like what we need. So we write G tau nu as a finite disjoint union of strings, all having direction epsilon 1 in this case. So we want to apply the theorem, then we write the eigenvalues of the Casimir, then the condition that the eigenvalues be different is given by the quadratic form, but below has to be different. So we get the following condition, that if G is SO to N, K is SO to N minus 1, and we have tau mu with, in terms of sum of bi's, epsilon i's, then we assume that the quadratic form 19 represents different numbers on the given set. Then in that case, the strong representation converse is valid. And then in this corollary, we see that given mu with such a shape and under those conditions, either B1 less than or equal 3 or condition 2i or 3i, then the strong representation spectral converse is valid, and then we have infinitely many cases where it holds. Well, now the opposite is that there are many examples of sets of disjoint strings, totally disjoint, having the same set of eigenvalues. So for these cases, we can show that the condition in corollary 7 is optimal in the sense that in these cases, the corresponding eigenvalues are not tame, and then we cannot obtain the strong representation spectral converse as a consequence of our main theorem. Well, then we can give explicit examples of that for all groups. There is an important case where the converse holds for P forms. We have looked in detail at the case of tau is a P-form representation, and then in the case of the sphere, this holds, but already in the case of CPN, the complex projective space, it holds partially. I mean, we cannot assert it holds completely. So this information...
The time is over. Are you concluding already? Or?
I just mentioned the study of the representation spectral converse, the last sentence. For mu not satisfying the conditions requires additional techniques that allow handling infinitely many non-tame eigenvalues. Thank you very much.
Thank you very much, Roberto. Is there any question? Okay, if not, we thank Roberto again